this computer. Okay. So let's share the screen. Why can't I share my? Okay, can y'all see that?
Yeah, we can see that.
Cool, cool. Okay, so this will be an intro to CFD. Kind of a basic overview. I don't want to go too far into the, I guess, technical theory. This is mostly to get you an understanding of how it works mathematically and in general. We won't get to how to actually do it until next week because you kind of need to understand all of this before you can start the plug and chug section. So I guess we'll start with an overview. So CFD studies, a typical CFD study, what you can normally expect to get or what you're going to try to get is some sort of drag force or coefficient. Typically, it could be a truck or a plane, maybe some kind of wing. A very common study is on an airfoil, different velocities, different angles of attack. Maybe you want to see the turbulence of water inside of some sort of pipe configuration. You can do that, or find the pressure of a pipe, pressure of flow inside of a pipe. You can also sim explosions, combustion, jet engines, rocket engines, detonations, stuff like that. Those are very typical CFD studies that, yeah, pretty common in industry and what you can expect to be doing once you learn CFD. There's also a difference between internal flows and external flows. CFD, you can do fluid flow that's happening inside of some sort of component, or you can do it that's where it's flowing outside of some component. External flows is mostly what we'll be doing because we'll be simming a rocket through midair. So air will be flowing externally of the rocket. Internal flows would be if we were maybe simming some sort of engine where there's some sort of nozzle. We have to simulate some sort of fuel going through the nozzle and expanding and whatnot. So those are the two main different types of studies, and we'll be dealing with external compressible flows, and I'll go into what that entails a little later. That's some like pretty deep theory. Feel free to stop me wherever. If you have any questions, please be sure to let me know. I may not know the answer because I am not an expert in this. A lot of this is just Googled over the course of the couple of years that I've been trying to learn CFD. So be sure to ask any questions that you have. We'll start off with an overview of FEA. If you're here for my first FEA workshop, I kind of go over what everything is, but I'm assuming that maybe you guys don't quite remember it. It's good to drill this into basically finite element method is a type of method to discretize some sort of region to make to solve some sort of physical problem or some sort of physical phenomena. So you break down the problem into some sort of finite pieces, which are the elements. So you can see here is a bunch of squares. Each point between the squares is a node, and you can solve an equation there. So the problem is what you want to sim, and the pieces are your mesh. This is what's called a mesh. Basically, you just take the air around an airfoil. You can see right in the middle is an airfoil, and you break it into a ton of tiny pieces where you can actually solve an equation per piece. And ANSYS uses what is called the finite volume method. And this is different from the finite element method. You guys don't have to worry too much about this difference. But if you do, it's an important difference. If for your understanding, it doesn't change how you solve anything. Basically, the main difference is if you guys are familiar with partial differential equations, finite element method solves the weak form of the partial differential equation, while the finite volume method solves the what is it? Shoot, I can't remember. It's not conservative partial differential equation. Oh, conservation form of the partial differential equation. So you don't have to know what those differences are. Just know that they are different. CFD uses finite volume method, structural dynamics, structural analysis, FEA, finite element method. These are two very different methods. So just keep that in mind. Okay, so how CFD works, we're gonna go into some aerodynamic material, some sort of or some aerodynamic background and theory. So just for your information. So Navier-Stokes describes all fluid motion. It's in its basic form, just conservation of mass, basically the continuity equation right here, and then conservation of momentum per degree of freedom, and then conservation of energy. So there are incompressible and compressible forms of the Navier-Stokes equations. You don't have to worry too much about what these are, but if you're familiar with compressible flow, you just include more terms in the Navier-Stokes. That's kind of it. Incompressible is just an easier, simplified version of the Navier-Stokes equations. And yeah, these Navier-Stokes equations can be used to describe all characteristics of fluid motion and the exact velocities, momentums, displacement of every single particle of air, water, etc. that's going through whatever flow region that you are in. The drawbacks of solving this is it's kind of impossible to solve it exactly. This is actually one of the, I guess, million-dollar questions in physics, is solving this exactly. Mathematically and physically, if we were to solve an entire flow region using Navier-Stokes equations, can we replicate that? And the answer is really no, because we have no way of knowing if this is exactly correct, 100% mathematically, to what happens in nature. You know, we could try to, I guess the example people like to use is, if you drop water from a cup onto a table, you can describe what happens using Navier-Stokes, but is that going to actually happen? Is every single particle going to move the way that Navier-Stokes described it to? And the answer is pretty complicated, but essentially, no, we cannot, we don't know how to 100% describe fluid motion. There's a lot of interesting videos online about the Navier-Stokes equations, how they work, why it's such an interesting question for physics and fluid dynamics and math in general. But yeah, this is very important for all types of fluid dynamics, especially CFD, and it's what we'll be breaking down today. Because we're going to start here, this is the main thing, and we're going to simplify it, and then we're going to convert it into a way that the computer can actually process it. And then we're going to have our results for some sort of fluid problem. So let's talk a little bit about laminar versus turbulent flows. These are two different types of, I guess, types of flows where if you look to the right real quick, laminar is just even flow, no movements. You can basically describe it as very, very even moving and like soft contours kind of thing. Flow around some sort of ball is completely uniform, doesn't change too much, not a whole lot of chaos, I guess you could say. And then turbulent flow is when you get these swirls, where you get these eddies. It's where it's kind of very disruptive and there's not a whole lot of uniformity to it. The main difference between these two, sorry, yeah, my throat's just not feeling great today. Main difference is the Reynolds number, which describes the inertial forces and the viscous forces. This is kind of a lot of terms thrown at you guys right now, but inertial forces is like the force of the ball, and then the viscous forces is like the stickiness of the air or whatever fluid you're going through. You know, what holds the fluid together, and is this motion stronger than what holds the fluid together? If it is bigger, or if it's larger by a significant margin, like if this Reynolds number is in thousands or 10,000s, it'll become turbulent. It'll just be thrown around, it'll separate, it'll turn into eddies, and it'll dissipate into energy. Oh, shoot, hold on. A little poem that kind of describes turbulence, because turbulence is one of the hardest things in the beginning to kind of get a grasp on, to really understand. And there's still a lot of debate on turbulence in general, how to model it, how to describe it. And I guess from a basic point of view, you can think of it in terms of this poem to the left. Big whirls have little whirls that feed on their velocity, and little whirls have lesser whirls, and so on to viscosity. So let's break it down. So big whirls are the eddies, the eddy vortexes, and each whirl takes energy from the other whirl that it's on. So big whirls have littler whirls, and that'll continue and continue until the flow dissipates into energy, or the viscosity of the fluid. It basically goes back into the fluid. The energy that made the turbulence just dissipates and dissipates and dissipates and dissipates until it just goes straight back into the air, or the viscosity. You can see that kind of better described here with the creation of eddy vortexes. And these big whirls have smaller whirls, and those whirls feed on each other's energy, which is then dissipated. So this turbulence, all of this, every single detail, all the whirls can be described by the Navier-Stokes equations, which is kind of crazy, but oh, let me just back up real quick. The scope of the Navier-Stokes equation. So the Navier-Stokes can describe all fluid motion, and I mean all fluid motion. So air around jets and whatnot, and then also larger scale, so climates and motion of air around cities, and describing I guess temperature and large scale things as well, which it's not just limited to tiny eddies and turbulence. It's got large scale capabilities to describe massive bodies of fluids as well. So that's kind of the scale of the Navier-Stokes equations. It's all fluid motion, to my understanding. I haven't taken a class in this or anything, so that's just kind of what I learned off of YouTube, and I can send everyone links if they'd like to learn more about the Navier-Stokes equation. But yeah, that's kind of the basic overview of that. Navier-Stokes, again, as we talked about, is impossible to solve exactly. It's also very computationally expensive to resolve theoretically. Like if we were trying to take all of these equations and then take all of them and solve them for every single node on this thing, which would take a long time, but it's actually kind of what some people do, which is what we'll talk about next. So turbulence modeling and numerical methods. So this is kind of where it gets a little bogged down. This might be the more complicated section of CFD. Let me know if you guys have any questions, but I may not be the best at explaining this stuff, so definitely make sure to ask if I'm not describing something very clearly. Essentially, we take Navier-Stokes and throw it into a computer, but how do we get there? So first thing we need to do is simplify the Navier-Stokes equations. And we can do that by using turbulence models. And I'll describe kind of how these change what you're solving for in the next slide. But you simplify Navier-Stokes by either doing no turbulence at all. So you just assume that the flow is completely uniform like this. Or you do Reynolds averaged Navier-Stokes, RANS. This is highlighted because this is what we're mostly going to be using. Essentially, we just solve a little bit and then we predict the rest of it. We don't directly solve it. We just predict it using some sort of model, some sort of turbulence model. And I'll talk about what those are later. But this is probably the easiest one to use, takes the least amount of time. What we'll be using on our rocket teams, and also the most it's proven to be pretty reliable. If you don't want exact answers, you just want to know how your flow is going to move around and whatnot, RANS is where you would go probably. LES, you solve for more things using Navier-Stokes and model less stuff using turbulence models, and then direct numerical simulations Oh, that's supposed to be DNS. Oops. That's basically solving Navier-Stokes directly. So you don't use any turbulence models. You don't fill in any gaps with predictions. You just solve it directly. And that's kind of shown on the graph over here. You can see that resolved means that you're directly solving Navier-Stokes, and modeled means that you're just plugging in an equation to predict what's happening in that area. And we'll be using RANS. So we only really need to pay attention to RANS. You can see that RANS solves for the injection of energy. So the start of the beginning of all energies, make sure that there's conservation of energy, and it models the rest of the dissipation. So the turbulence, how that energy is dissipated into the air. Here's a good video to show the difference between these three. DNS, as you can imagine, since you're directly solving Navier-Stokes, is the most accurate. It gives you the most detail, but it's also the most computationally expensive. It takes forever. You need super computers for this kind of stuff. Researchers only recently started using direct numerical simulation because we didn't have the computing power to do it. LES, RANS were the most practical ways of doing it. Pretty much all of aerospace uses RANS, or even less than that. So this is mostly practical, but in terms of research, this can sometimes be useful, DNS. This best illustrates the difference. You can see the top is extremely well resolved. There's a lot of detail in the eddies and the smaller whirls. And down here, you can see the bigger picture. It's not exactly inaccurate, it's just less detailed. So that's what you can expect using RANS. And this is what you can expect using LES, which is close to DNS, which is direct numerical simulation, but still modeled. So this is not even as accurate as you can get it. There is longer simulations which can get more accurate here. How do I? Oops. That's kind of an overview of turbulence modeling. If we go back a little bit, how does the turbulence modeling get described into the computer? How do you just plug in a differential equation? Because that's essentially what these are. These are just partial differential equations. Then you use what are called numerical methods, which is Euler's method, Runge-Kutta-4. These are just ways of converting your PDE into some form of linear equations. From there, you can use linear algebra or some form of matrix manipulation to solve your linear equations and get results for each node. Fun fact, Runge-Kutta-4, this is a common numerical method, and this is actually used in OpenRocket if you guys are familiar with OpenRocket, because I'm pretty sure OpenRocket uses differential equations, and in order to solve them, you can convert them into linear equations using this method. But that's kind of within the details. You don't need to remember that. You don't need to really know how that works. But you do need to know these ones, because there is a difference between each of these, as you saw in the video. Using this one takes forever, but it gives you better results. Whereas this one is more practical and it gives you an overview of the results. Maybe it doesn't give you enough details. You know, that's kind of up to you to decide. Also, what you're limited by is, can your computer actually run all this? It's something you have to consider. So start chat here. Okay, so turbulence modeling, again, turbulence models are good for certain situations. So you do need to know the different names of some turbulence models. Again, these are RANS models. These are the Reynolds average Navier-Stokes equations, these bottom ones. Alamaras, you don't need to memorize these for now, but just know that they exist. These are the three pretty much most common turbulence models that we'll be using. Here are some of the downs of using them and kind of the applications that you'd be using them for. Alamaras, it has one equation and is useful for fast and reliable aerospace applications usually. This was designed for aerospace applications, so it's used for that mostly for like drag and calculating drag coefficients and whatnot. It is bad for, it's bad for plotting accurate adverse pressure gradients. Essentially what this means is it doesn't show your flow separation very well, which is up here, you can see separation point, and this is where your flow will start to separate, and it's where you will create more drag, essentially. Flow separation, you want to happen later, farther back on your object, and that'll decrease the amount of drag your object has. If flow separation is farther up here, you'll have more drag, farther back, less drag. That's kind of why golf balls are pimple, have those dimples on it, not pimples. Those dimples actually help to push this separation point farther back, decreasing the amount of drag that golf balls have. Yeah, and Spaller-Almaras is bad at describing where this occurs. So don't use it if you're trying to find that. K epsilon SST, pretty similar to Spaller-Almaras, just more useful for, or more accurate for free stream kind of flows. All that means is it's useful for flows that are away from bodies. Anytime you have a body, it's pretty much considered a wall. So you can see adverse pressure gradients near walls, anything that's near some sort of rocket body, sphere body, etc. Those are considered walls. K omega is two equations similar to K omega SST. This is, or K epsilon SST, this is K omega, also K omega SST. Forgot to write the SST into here, but same thing basically. This one is useful for resolving effects near the wall. So it will tell you where the flow separation is with a reliable amount of accuracy. Any questions with these? Because I know it can be a little overwhelming. There's a lot of terms thrown in here, but do you guys have any questions about that? No questions? Okay. So let's talk really quickly about actually solving using some of the information that we've learned earlier. We'll talk about the mesh to begin with. Again, meshes come in all shapes and sizes. This is very similar to my FEA workshop, but important to know because shapes and sizes, more nodes, which is these points, longer solving time, but it is more accurate. So less nodes is faster solving time, but also less accuracy because you're using less points to solve for along whatever surface that, or whatever body that you're solving on. I'm just going to run through these pretty quickly. ANSYS softwares, don't memorize these, but good to know that they exist. CFD, we'll be using Fluent mostly, not CFX, Fluent and SpaceClaim. So SpaceClaim is the CAD software that ANSYS has. Fluent is the CFD software. So mostly these two. CFD workflow. If you're going to be using ANSYS, which I'm assuming you're here to learn, this is what it'll look like if you're going to do a CFD study. At the top, you see it's fluid, flow, fluent. So that's the type of study. It's a CFD study. You're going to import your geometry, your CAD. You're going to make your mesh, and then you're going to do your setup and solution in Fluent, as well as get your results. And Fluent, again, is the CFD software that ANSYS has. And Mechanical is the meshing software that ANSYS has. Oh, and then this little thing at the bottom, don't worry too much about this, but post-processing is essentially just taking your results and turning them into useful information, turning them into plots, contours, pictures. That can be done in CFD Post or TechPlot. These are just two different softwares that take your data and turn them into plots, contours, pictures, the pretty pictures section of CFD. CFD studies work exactly the same as FEA studies with your pre-analysis, setting up your geometry, setting up your mesh, setting up your model, getting your results and solutions, and then verification and validation. This is a lot of mumbo jumbo right now, but just think of this as understanding what it is you're going to do. Geometry and mesh is simplifying your, I guess, problem, making it actually possible to solve. And then model setup is making sure that you have an accurate way of going about your solution, making sure you're taking everything into account, that you know what you're doing. Validation, that's like wind tunnel stuff, actually testing your rocket midair. Yeah, that's kind of the main way of validating CFD, is sticking your object into a wind tunnel and seeing how accurate you are in terms of drag force, lift, etc. Pre-analysis, you take your physical problem, turn it into a mathematical problem. These are called your governing equations. So which RANS model are you using? Are you trying to solve for combustion? And then your initial and final values. So what do you feed the nodes? What is your starting thing that your computer is going to solve for? And what is the ending value that it's going to try to result into? You can give like velocity boundary conditions, which is your initial condition. And then you can say that there's some sort of 200 bar of back pressure as your outlet condition. Inlet being what it starts at. So it's going to basically push all the air here at 50 meters per second. And then it's going to make sure that at the back here, there's 200 bar of pressure. And then everything in between it solves for. So it knows this one and it knows this one. So it's going to solve for everything in between. CFD geometry, essentially, you can simplify what it is you're solving for by pretty much deleting everything inside of your rocket. Or if you're doing an external flow, you don't need, electronics CAD, or you don't need brushed structure CAD, stuff like that. Screws, bolts, nuts, those just make your analysis harder. And you can just delete those typically. You want to change your geometry to have simple and efficient meshes and accurate results. This is just part of the whole efficiency thing, making sure that what you're doing isn't going to take forever or crash your computer, stuff like that. And you're basically going to ask yourself, what is it exactly that you're trying to find? Is there something that you're trying to find that will be affected by your geometry? How does your geometry affect the flow? Don't delete, basically in the big picture, just don't delete your rocket's fins or something. Or if you're trying to find your air brakes, don't delete your air brakes or anything that sticks out of the rocket significantly. Is it necessary? If it's just a design thing, you can mostly get rid of it. These are just case by case, but know that a lot of the time you don't need the whole CAD to do CFD. You can delete some of the smaller details. A big part of CFD, kind of the main way it's different from FEA, is that you CAD the air. You don't CAD the inside of your Formula One car. You don't CAD the inside of the rocket. You CAD the outside air, and then you solve for each point there, each point of the air. Basically, you can kind of think of it as a massive wind tunnel. You need to CAD the outer dimensions, and then you need to CAD the outer profile of your rocket. You don't need the insides, just the outside. And then you'll mesh everywhere in between. You can kind of see here the cutout. Outside is a big box where the car sits inside, and you'll mesh all the parts inside of it. Some ways you can simplify your geometry is by cutting it along a symmetric plane. This is a very common practice. Is what we're going to be doing a lot, where you just cut your thing in half and say that it's flipped. You can do this quite a lot. If this car is symmetric halfway across, just cut it in half, and then you can use less nodes, half the number of elements, basically. Makes your solving a lot faster. Definitely 2D versus 3D is the fastest way to get faster results. You just have to simulate the outer contour of your car. You can totally do that. And then simulate airflow around it, which can give you basic results. So it's not going to give you the most accurate overview of what's happening to your rocket or to your car, but this is the way of getting some fast results easily. And it's what you'll probably be practicing a lot when you begin CFD. Don't just jump from 2D to 3D, or don't just jump straight to 3D. I mean, definitely do 2D, and it very easily transfers into 3D, but it's way faster to do things in 2D. This is one of the biggest things that you'll be doing. Space Claim is ANSYS's CAD software, but they specifically have features that prepare CAD for CFD, and we'll talk about those some other time, but there's a lot of useful things that Space Claim has, which you can do all this for. Well, not the 2D part, but you can cut it along and say that there's symmetry. You can fill in the inside. So if you have a hollow rocket, that's not really going to work out too well for the meshing. So you can fill it in with just CAD's solid bodies, or you can hollow something out if you needed to. And Space Claim has those options. You generally want to make CAD for CFD. See this car here? This car has absolutely no details. It's just the outer contour and some of the major parts. That's kind of what you'll expect from a typical CFD simulation. No details, just the contour, just the parts that'll affect the flow. And yeah, nothing too crazy for CAD in terms of CFD. Really, really simple. The mesh, again, there are different types of elements. I won't go too far into what these are, but using different ones can increase your accuracy, but they can also take longer to solve. Mesh metrics, there are ways of telling if your mesh is good enough for certain things, and that's given by these different factors. Your computer will tell you what each of these are. It'll actually rate some of them on a scale, and you can go in and see whether or not your mesh is actually good based on these parameters. And then you'll have to fix it from there. Structured versus unstructured meshes. CFD prefers kind of structured meshes near whatever it is you're solving for. So you can see on this triangle, it's a very uniform mesh in front and a very uniform mesh behind. This is pretty typical. It's what you'll want to learn how to do. This does take a good amount of skill in the beginning to figure out. Meshing is one of the longest time sinks in CFD. You're going to be spending a lot of time just making this look nice. And then the rest of the time is just spent waiting for your computer to finish. So structured is harder to make. It's more efficient, less nodes, shapes the geometry well. Yeah, you're going to want to aim for this. Unstructured is really fast to produce. You just click a button and it does this. This is what SolidWorks does. And it's kind of why it's not the most reliable CFD FEA tool. But sometimes it's necessary to do this, but we won't really go into details about that until you begin trying that on your own. Because using one or the other is a case by case. You'll figure out what's necessary depending on your part. That's pretty much what I had for now. I don't want to go into an example quite yet because one, it'll take a while, and two, I think that was enough information already. So do you guys have any questions about anything I've gone over so far? You want me to review anything or?
Yeah, could you review the Reynolds number part where you talk about, yeah.
This one, yep.
So what did you say regarding this for turbulent flow?
So the turbulent flow is basically, by definition, when inertial forces dominate viscous forces. Inertial forces are the forces of the ball, let's say, or your rocket. It's kind of what force this object imparts onto this fluid. And the viscous force is what holds the fluid together. It's like how sticky your fluid is. And if the Reynolds number is really high, in the thousands, let's say, it'll become turbulent because your ball is basically tearing apart the air. I guess that's maybe not the best way of describing it, but it's a good way of visualizing it. The air is no longer able to really hold itself together with its viscosity, and it just gets thrown around like this. And then the energy that this ball imparts into the air becomes dissipated in eddy whirls, which you can see here. So let's say this ball is just bashing into the air. It'll create these waves, which have smaller whirls, on top of them. And the energy of this ball gets put into this wave, which is then transferred into a smaller wave, which is then transferred into a smaller wave. That just keeps going until it no longer has a wave. It just turns into heat energy. That's also why something moving super fast generates a lot of heat. Not only is there skin friction, but there's also a lot of energy from turbulence. I believe that's something I think happens. I am not a fluid flow expert, and I've not taken a class in this, so that's just pretty sure that happens. Any other questions? Nope, I think that's everything. I'm gonna stop it here. Need me to review anything or anything else? I guess ask now. Otherwise, you're free to go.
Thanks, Alex.